My name is Mihai Bilauca from University of Limerick, Ireland. Thank you for the introduction to Andrew. Today I'll be presenting a paper on building table formatting tools. Just to give you an idea of, I'm going to stick within the given time. I have 48 slides, don't worry. Some of them are just lots of images, and I'll be flying through them. There is a little counter at the bottom of the presentation in case you wonder where am I about and how long do you still have to wait until I'm finished. Why this paper? Tables are widely used for presenting logical relationships between data items. Interesting enough, the widespread of WYSIWYG tools only allows us to control typographical parameters, and very little control do we have around the structure, the table structure manipulation. Have you ever tried to rotate a table after you realized it doesn't fit into your page and you have to rotate the other way around and see how long that's going to take, and also see how many errors can you actually introduce when you try to do that? Also, the existing tools have limitations. Last year I kind of highlighted a couple of the problems that existing tools have, from Word to OpenOffice to other word processing tools that we currently use. And you probably know that authoring tables is hard, time-consuming, and error-prone. During the presentations, I'm going to look at a review of the logical table models. I will be presenting a table drawing tool prototype, and in that context, typographical issues. The table drawing tool prototype implements an automated table layout optimization for tables with spanning cells. We are reporting on experimental results for large tables. We are making a comparison with the previous models that we have published. And we are also providing a simplified solution for nested tables. And we are going to draw some conclusions. So logical table models, being able to control the table at the logical level, as I said, presents a couple of advantages that have been already documented. You know, as I said earlier, you are trying to rotate a table once you realize it doesn't fit in the given page width, and you realize this is going to take me forever to do that. You know, so. One of the first people to look at a logical table model was Beach in 1985. He actually presented a model where the table was in fact a grid that had a table topology and a table geometry. Beach has defined that as the table as a abstract object in a Tioga document processing system, and the object knew how to format itself based on given dimensions. In 1989, Cameron identifies three mental processes in table editing: structural editing, content editing, and visual editing. In 1989, Van Arbik came with an interesting way of defining tables using a language based on attribute grammars. And basically, Van Arbik looks at tables as a multidimensional collection of logically connected data items. Each dimension is divided in rubrics to classify data items, and measured items are being used where an item is connected to multiple rubrics. I found interesting the way Christine was able to link the typographical parameters to the data items using this language-based on attribute grammars. In 1996, Wang, in the PhD thesis, presents the layout, separates the layout structure from the logical structure, and Wang is using a mathematical based on unordered sets. They identify operations at the table, category, and label level. An interesting model was introduced by Parnas, where tables are not only just data items, they are in fact meaningful expressions that can be evaluated and validated. Parnas is using indexation to separate the table semantics from appearance. And basically, a table is an index set of grids, an index set and a mapping between the two. And every grid, in fact, is an index set of expressions. And again, an index set and a mapping. The reason I went quickly through this logical table models review is to see how the requirement to be able to manipulate tables at the logical level has actually evolved from a simple grid to a set of expressions that can be evaluated and validated. To discuss a table drawing tool prototype that we have actually been working on in the University of Limerick. The table drawing tool is a part of a larger project that was supposed to deliver a tabular expressions tool. There are 4 modules part of this tool. The table input tool that's concerned only with the problems arising from data entry. A kernel that's concerned on how to hold all the data and its implementation. An evaluation module that guides the user in making sure that the expressions are complete, in evaluating the expressions, and a table drawing tool which I've been working on for a while. And the concern of the table drawing tool is to simply draw tables. And the way the table drawing tool works is it renders tables depending on their layout on a rendering device using a layout optimizer. The current version supports rectangular tables which can be rendered in PDF using a layout optimizer that's using an IBM iLogs optimizer. Why am I saying a rendering device? Is because all these objects are abstract, and the idea is that they should be independent of each other. A circular layout. What's that? A circular layout for a table. Have a look at the table 1, for example, and you can see that the same way the same table can be represented in a different shape. Obviously, the circular layout in this case will pose totally different sets of problems when it comes to drawing that. Cells are no longer rectangles. As you can see, they're of a different shape. Their arrangement is different. So maybe it's not the best example that I can come up with. But just to say that tables or arrangement of data can happen in any shape. And that's why the rendering tool is, in fact, as I said, rendering tables of any layout type on any rendering device using optimization and an optimizer. What's a device? So a device is an abstract object that must provide functions to open and close the device, set colors, fill colors, line styles, font settings, vertical and horizontal alignment, draw curves, has to support images and support for paging the content. The device must return measurement units in the coordinate system used by the tool. The device has, in fact, to know how to deal with its own parameters and expose those parameters out to the tool. TDT implements a hierarchical model. Why is that? Because a table tool needs to be as powerful as a page layout tool. In a table, you can have any type of objects layout in various ways. You can have fixed positioning containers. You can have floating positioning containers. And a hierarchical model allows us to control the hierarchical propagation of typographical parameters. That means you don't want to set up your font size at every cell level. You want to set it up at table level, and then the cells will inherit the font size from that. And also allows us for layered control of typographical parameters. You know, you may have objects that overlap, and you want to determine, or you have to let the user to decide which ones should be, which object should be visible when they are overlapping. It is each container's responsibility to format itself. In fact, every container should know how to draw itself to a rendering device. The rendering device should return whatever information the container requires to render itself. For drawing tables, the table drawing tool implements a box model, similar to the box model implemented by the CSS. The box model allows us to have a margin space, a border space, a padding space, and a content space. However, using this model, there are a number of typographical issues. We have to deal with the table layout, which has a caption in a layout. The caption is normally placed on the top, but it should be down to the user whether he wants the caption to the left, to the right, or to the bottom. The layout can be, as I said, rectangular, circular, or a custom layout. It can be of any shape, in fact. The caption, you have to have a label, a number, and a caption text, but obviously you have to define a global numbering styles. And you have to have some rules around how these captions should be displayed. They have to be in a consistent way. Laying containers, you have to work around laying containers. They're fixed and floating positioning. We are implementing in table drawing tool a method where we are laying floating containers on lines. And obviously when you have fixed and a mixture between fixed and floating containers, complexity of the arrangement algorithm is increased. Lines, you have to define lines, styles and joins, the patterns, and you have to work around the margins. When you have containers next to each other, should the margins be added? Should they be adjacent? Should they be merged? And all these questions, all these issues that you encounter while you're trying to program the drawing tool, you have to deal with each of them individually. In the table drawing tool, the coordinate spaces, we implement a coordinate space where the unit is similar to the point definition as being 72 part of an inch. You have to deal with the text direction, right to left, top to bottom, especially if you need to rotate the cell's content. Equations, how to render equations. TDT implements WebAQ it's an API that renders MATML expressions. When dealing with images, you have to convert from pixels, or whatever units the images are coming with, into the units of the coordinate system you are implementing. And I left borders, especially at the end, because borders cause enough lot of problems when you are trying to alter a table. You probably have experienced yourselves all these issues around borders. And you have to deal with the border space, with the border alignment and border priority. And just to give a quick example as what happens when you are dealing with borders, this is an example from when I was using OpenOffice. You can probably see that cell A1 here is, for example, cell B2, the border is actually overlapping over the text. That's because the border space is taken from half of the border space. No, the border space is taken from the inside the cell, and that's why it overlaps over B2 here. And also it's a bit inconsistent because it seems like the B2, the cell B2, has priority over cell A1, but only for the left and right borders, not for the top one. The number of problems that you actually encounter when you're looking at only at how to deal with borders, it isn't funny. Also, if you look carefully, the bottom border is actually taken from the next cell. The space for the bottom border is taken from the cell beneath that, while the border for the right is taken half from one cell, half from the other cell. I mean, all these kind of small, minute details are what actually makes life very, very difficult when you're trying to draw tables. And that's only talking about borders. There's a whole range of problems when it comes with dealing with margins. I'm not going to spend any more time on this. I reported on some of these issues in a previous paper I presented last year at the same conference here. In the same tool, we are implementing automated table layout. And why automated table layout and why table layout optimization is because there are applications where you need to know precisely the layout of a table with the minimum height for a given page width. Imagine if you want to print a book and your table jumps only one row on a different page, you have to add headers, another page, and so on. So you have to find out what is exactly the layout of a table with the minimum height for a given width. Also, when we are optimizing layout, we are giving priority to the user imposed constraints and other statistics criteria. In the way we are modeling the table layout optimization, we're adding other constraints to the model in a very easy way. So the table layout problem basically says finding a layout of a table with a minimum height such that the page width is that its width is less than the page width. Anderson and Sobti gave a formal definition of the problem for tables that contain text. And basically, don't be put off by the amount of mathematics and indexes. I will try to explain in a natural language. Basically, every cell has a number of text, has a number of configurations, and the idea is to select from each of these cell configuration that configuration that will actually minimize the table height for the given page width. And as you can see, what's the cell of in this case, the set of cell configurations, there are 3 configurations, as you can probably see here, and that's the set. If we are to give an integer programming definition for simple tables, that means tables without spanning cells, it's minimize the height, and the height of a row is given by the maximum of cell heights, subject to the page width, the table width to be less than the page width, and using some binary variables x. Okay, so basically for every configuration k in a cell, we have a binary variable that selects that configuration. For tables with spanning cells, we are introducing new variables. We have 2 arrays where S, H, and SW here, where the number of we are storing the number of additional rows spanned by each cell and the number of additional columns spanned by each cell, and therefore the height of a cell is the height of the cells that it spans, and the same way the width. We identified 2 cases. We have a case in the case A where the cell 1,1 spans wide columns and cell 1,1 spans narrow columns in the second image. And what we are saying is that to solve the problem where the cell spans narrow columns, we introduce the concept of glue. Glue is something similar to the way Knut has introduced glue in paragraphing. It shrinks and expands depending on as required. We are introducing glue because it can be further constrained. We can say, look, I want to have the glue distributed equally, or some other constraints around the glue. You can probably see here it's slightly grayer, that extra space that's required to actually feed the text correctly. Therefore, the height of the cell and the width of the cell is it's the sum of the spanned cells plus the glue for each of the columns. The integer programming definition in that case is simply using binary variables. We are computing for every column, we are computing the set of possible column widths, and for every row, the set of possible row heights. We are using 3 binary variables, x, y, and z. You are probably going to see it through our presentation, and they are being used to select that cell configuration that's actually less than the selected column width and the selected row height. So as you probably have seen, you can see now the new integer programming definition for tables with spanning cells is to minimize the height of the table or using those row heights that have been selected and their glue, subject to a number of constraints, such that every cell is less than selected. As I said earlier, every cell's width is less than the width of the column, and every cell's height is less than or equal to the height of the selected row height. Of course, for every cell, as you can see in constraint 4 here, in every cell, only one configuration needs to be selected. And in every row, only one height has to be selected. In every column, only one width has to be selected. In order to be able to deal with constraint 4, we are introducing for cells that have been spanned, which obviously have no configurations, we are introducing dummy cells. They are basically cells that have a width and a height equal to 0. And therefore, constraint 4 is expected for all the cells in the layout. This table is MP complete. It has been demonstrated by Wang in 1996 and Anderson in 1999. Therefore, we are using a optimization programming language, OPL, to solve the problem. We are providing a model we've chosen OPL because it supports mixed integer programming and constraint programming. It supports logical and higher order constraints, and it supports scheduling and resource allocation applications. That wasn't for our purpose, but as a presentation of OPL. It shares structures and syntax features with mathematical programming languages such as AMPL or GAMS. And what's important is that problems can be formulated in a language similar to their algebraic notation. And so it's very easy to follow what I just presented in mathematical formulation into the programming language. Just quickly to demonstrate the model, I'm going to introduce a couple of keywords. dvar is a decision variable, and the purpose of an OPL model is to find values for those decision variables. An expression is an expression decision variable in a more compact way, and between curly brackets, it's a set of data type. And we have a tuple. So how we have actually formulated the model, a couple of data types. Initially, we have conf and cell conf. Cell conf is that contains 3 integers, the I, the j, and the width and height of the cell. We have a set of cell configurations, as you can probably see. And then we are determining the set of cells, the set of rows, the set of columns. We are computing, therefore, the set of possible column widths by excluding the spanning cells. Obviously, they span over a number of columns. In a similar way, the set of possible row heights. We introduce 3 decision variables, as I explained earlier in the mathematical model. X for selecting cell configuration, Y for row heights, and Z for column widths. And also two other variables, the horizontal and vertical glue. The cell width is expressed as a product of the width of the cell and the decision variable that has been found. Similar way for the row height and for the column width, they are binary variables, and the sum and the height of the table are just simple sums of those row heights and column widths. And the problem is to minimize the table height, where the following constraints need to be respected. Table width has to be less than the page width. Then each of the values that are selected for the cell and rows and columns have to be selected only once. To choose for each cell a height and a width, we have to make sure that they are less than the sum of the columns or row heights and the glue for each of those row heights or column widths. It's the same for column widths. The constraint for column widths is similar to the constraint for the cell heights as it's presented at the moment. One of the things I mentioned earlier is that we can constrain the glue. I mean, how do we want the glue to be divided along the columns? And that is a way to actually constrain the glue. We are basically distributing the glue over the number of columns that a cell spans. And there may be other ways of dealing with it. When it comes to experimental results, we have actually improved on the TSC model that we are reporting on has actually improved time compared to the previous models we have published last year. As you can see in a table that was 30 by 30 with up to 6 words in each cell, the running time came down from probably an hour and a half down to under 10 seconds. Here we have some other experimental results for even larger tables. With this model, we are now able to report to tables that have up to 3,600 cells. I'm going to show a couple of examples earlier that in the next slides. For example, for a 40 by 40 table, we had a case where the running time for the previous model was an hour and 26 minutes to solve. Now that has come down to about 2 minutes. And again, with the previous model, we weren't able to report on even larger tables than 40 by 40. Just the running time was, we just couldn't report on that. But now we have some good results. Just sample output, how does it look after it's being optimized? This is just an example. Now we also have an example for nested tables. Dealing with nested tables when it comes to optimizing the layout, it's quite tricky because our model is based on knowing a predefined set of possible configurations. Obviously, a table will have a large number of configurations, and computing the number of table configuration takes time, you know. And also, every change in the table configuration will actually, in the inner tables configuration, will change the whole configuration of the parent table. Therefore, a quick solution is to actually embed the inner table into the table by considering the inner table as being part of, by merging or considering the table as being, or considering the cells where the merge table is as being merged. And therefore, the inner table becomes part of the outer table, and therefore the cell configurations of the inner table are taken into account for the larger table. This is an example where you can see how the inner table has actually been embedded in an outer table, and the model that we just defined applies for it as well. Obviously, if the inner table has now a caption and has other elements around it, it's not going to be as easy to deal with it. I'm going to show you just to see how a table that's 40 by 45 with, if you can zoom in and see how large it is. By the way, this page is A0, so it's probably a meter if you are to print it, and how the layout looks when our tool has optimized that. We have a couple of mesh cells here. And just to draw some conclusions, building table tools is hard because tables can contain any type of objects, text, images, mathematical expressions, and even other tables. Operations at the table structure level are hard and prone to errors. WYSIWYG tools are concerned with presentation only. Using a flexible presentation model, such as the hierarchical models with the box, raise a number of issues, and I've explained some of them. The model we've presented is faster, and we are now able to report on larger tables. Computing test configurations, in other words, the paragraphing problem, is critical for this model, and it is time-consuming. We can constrain the glue for tables with spanning cells. And we have suggested a possible simplified approach to solving the layout with nested tables. We are intended to work further on the nested tables, and we are looking at other users' constraints, for example, constraints on a group of rows and columns. And that's it. We'd like to express our gratitude to Professor David Parnas for motivating much of this work. And I'd like to thank Kim and Graham for providing feedback on this paper. Do you have any other questions?
Mihai? I have a question. I'm going to get the microphone and ask them to show how it works. On nested tables, I wasn't quite sure whether you mentioned that the
the table that was nested, whether that's as a static object or whether you actually relay out that table or re-optimize that table.
It was, what do you mean by a static object?
Just an object which doesn't change, just gets embedded.
Well, I'm not sure exactly what you mean. It doesn't change. What do you mean that? Like,
Do you actually apply the algorithms to that
yes,
inner table?
What we actually do is that table becomes, the cells of that table become part of the cells of the outer table, and therefore the cell configurations for the inner table are now a set of the outer table, and any change in those configurations are taken into account when we are computing the outer table. So obviously it's part of the larger table.
As another question, it's clear to me how nested tables are difficult. The kind of recursive structure could be nasty. But is there other content? You talked about other kinds of content, and I'm kind of intuitively wondering whether mathematics is trickier somehow than standard text, because your examples are standard text. Is there other material that would cause you more trouble?
Mathematics, as I said, through the tool we are rendering the mathematical expressions. Of course, they will be more difficult. You know, the rules around mathematics are totally different than arranging text. For mathematics, we are using an API that converts mathematics into JPEGs or GIFs, okay. And that's fixed size. They don't change. Okay.
So if you were to really retypeset the mathematics, that would be a hard problem. The idea is that the input is totally different than the output. We are not looking at a WYSIWYG tool here. We are looking at a tool that allows you to do your data entry. It gets stored in the kernel, evaluated, so the tool should be able to tell you if the mathematics are, the expressions are correct, have you provided enough information, and then drawn out. It's not a WYSIWYG tool. Sure. Thanks.
Thank you. Sorry for...
There's one more question, actually.
Mihai, yeah, one more question. Do you have any idea why your new model is so much faster than the previous model?
Yes, in the previous model we weren't constraining the row heights. We were working only with the set of column widths. So now we have further, we are further constraining the problem. So we haven't used the row heights at the time.